factoring special products. And so for the first special product we want to look at, first I want to take a step back and look back at multiplication. So if we have a binomial times a binomial, so for example, here I'm going to do x plus 3 times x minus 3. So when you're multiplying a binomial times a binomial, that is where I multiply 4 times. So I multiply x times both of these terms, and I multiply the 3 times both of those terms. And a popular order to multiply in is people like to say FOIL. So I'll do the first term times the first term, so I will get x squared. Then I multiply my outer terms to get negative 3x. I'll multiply my inner terms to get positive 3x. And then I multiply the last term in each binomial to get minus 9. So what happens here, because this was a special product, what happens is that these middle terms, when I combine like terms, they cancel out. And so I end up with just x squared minus 9 when I multiply. So the multiplication isn't really usually an issue. It is the reverse when we are factoring these that it can be a little trickier, because this, upon first inspection, does not look factorable, but we actually know that it is factorable. It can be written as x plus 3 times x minus 3. So the first special product we're looking at today is called a difference of squares. And so couple keywords here, difference. So difference means subtraction. So whenever I am subtracting, so notice in all of these examples here, I am subtracting. And then the next keyword here is squares, so perfect squares. So when you see numbers like 1 or 4, 9, 16, 25, 36, so forth, these are all perfect squares. And what I mean by that is 1 is 1 squared, 4 is 2 squared, 9 is 3 squared, 16 is 4 squared, 36 is, and so forth. And so whenever you have two values that are both perfect squares and you're subtracting them, they can be factored. It's a special product. So the general rule says if you have a perfect square minus a perfect square, in this case a squared minus b squared, you factor that as a plus b times a minus b. And so the first example, I'll add an example here. So I will say maybe x squared minus 25. And so upon first inspection, like I said earlier, it doesn't look factorable. There's no common factor. It's not a trinomial. But you just have to be aware that when you're subtracting two terms like this and they are both a perfect square, that is x squared and this is 5 squared, that you just kind of have to remember that those can be factored as x minus 5, x plus 5. So I took the square root of x squared, the square root of 25. And if you weren't sure, I could distribute here, I could FOIL, and I would get right back there. So for this next example, I notice it's a difference, it's subtraction. 9 is a perfect square, it is 3 squared. X squared is x squared. And 16 is 4 squared, so everything here is a perfect square. So I remember the pattern here, so it's going to be 3x plus 4 times 3x minus 4. Or 3x minus 4 times 3x plus 4. Doesn't actually matter where I put the plus and where I put the minus, because the binomials are the same otherwise. And so if I were to FOIL that, if I were to distribute, I would get right back to where I started. So that's what makes this a special product, is that it might not be obvious just by looking that this is factorable, but because everything here is a perfect square, and because it's subtraction, it is factorable. So you might want to pause it and try the next one, play the video and see how you do. So if I look at this binomial, I notice they do not have a common factor I can factor out. It's not a trinomial, But I do notice that 25 is a perfect square. That is 5 squared. N squared is a perfect square. 81 is a perfect square. It's 9 squared. Or the square root of 81 is 9. And it's a difference. It's subtraction. So here I'm going to get 5n plus 9 times 5n minus 9. And again, I could switch the order I wrote these two binomials, since it's multiplication here in between. So if I were to FOIL these, I were to distribute, my outer terms and my inner term will cancel out. And that is why I only get 2 terms. Okay, so this last one, it doesn't appear to be a perfect square, or sorry, a difference of square here. That's because it's not yet. So the first thing you hopefully check is to check for a common factor. So when I look at these two terms, I can see, oh, 2 is a common factor. So if I factor a 2 out of each of these, I get 2 times 4 minus 9g squared. So once I factor, I can see that 2 is just a 2. But this part in parentheses here is now a difference of squares. This is a perfect square. It's 2 squared. This is a perfect square. It's 3g squared. So I have my 2 and I leave it out there. But then to factor the part underlined in purple here, I would get 2 plus 3g times 2 minus 3g. So that is the first type of special product, and it's called a difference of squares. And then something I just kind of want to warn you about while I'm thinking about it is that if I had x squared minus 25 over here, if that said x squared plus 25, if that were not a difference, if it were a sum, so if I try to trick you here and put a plus instead of a minus, then that would be not factorable. Not factorable. Or a word for not factorable is prime. So notice if it wasn't a difference, if it were a sum of perfect squares, it would not be factorable. So the difference of squares, that's what we just looked at here. And the next one we're going to look at, the next special product, is a perfect square trinomial. And so the general rule says a squared plus 2ab plus b squared is going to be a plus b times a plus b. So it's going to be a plus b times a plus b, which, kind of a key important thing here, is when you have something times itself, you can just write that term a plus b squared. So right now that may not have made a whole lot of sense. It will actually make more sense when we look at it with numerical values over here. So if I look at this example, if I go to factor this is from a couple of units ago. It's a trinomial. They don't have a common factor, so I can kind of do that reverse foiling. So if I look and I think, okay, what times itself will give me x squared? I know it's x times x. Then I look at what times what will give me 9, but combined to give me 6, and that would be 3 times 3. 3 times 3 is 9. 3 plus 3, when I combine like terms, will give me 6. So I get x plus 3 times x plus 3, which is correct. I have factored that correctly, except the thing that's calling this, making this a special product, is that it's that binomial times itself. So that would be written x plus 3 squared. And so for the next example, so notice example 17, I cannot factor anything out of all 3 terms. So I could do this by grouping. I could, or you might notice that it kind of follows this pattern. So I could see, okay, what binomial times itself will give me this? So what times itself is 4g squared? That would be 2g. 2g times 2g. I also noticed that all three terms are positive, so I know it's going to be a positive times a positive. And then what times itself is h squared? It's going to be h times h. So notice I have a binomial times itself. And so the way to write that is to write the binomial once, 2g plus h, and then note out with an exponent here that it is squared. And that is it for special products. Notice and remember that there are also additional videos on MyLabs Plus if you need them.